Okay, so welcome everyone. It's a pleasure to have Akshay here today as a speaker. So Akshay is a faculty member at IIT Bombay, and he works on several areas in formal methods, particularly quantitative verification and synthesis in timed automata Markov decision processes and Boolean function synthesis. So today he's going to talk about Markov decision processes. And it's a rare day in SCCS because we had another talk in the morning on MDPs.
No, it's a regular MDP day, and
It's like
but I should have taken a decision.
so yeah, forgot your thanks.
Thanks so much. Thanks everyone for coming up, and thanks Shivaji for inviting me. It's great to be back here. Can I say? I mean, my first encounter at AIFR was 2002. No, as an undergraduate, as part of the VSRP program, one of the amazing programs I think which is running there. And since then, I've been coming back and forth, but I've actually been stranger for the last 9 years. Looks like so. It is very nice to come back here and see so many faces, like so many familiar and many new faces. Hey, one more. One more. I see them and I'm like, I should have come here. Clearly, I should come here. Yeah, it's a pleasure to be here. And it's also, I'm very happy to give this talk on Markov decision processes as distribution transformers. And as somebody pointed out, this is not any of the transformers maybe that you know, right? I mean, this is neither the transformers from ML nor as we pointed out the transformer down the hall, which keeps the electricity on or whatever it is, right? So, but we'll go into why this view is interesting, and I want to kind of give it formal methods a point of view on it. And this is really joint work with Krishnendu Chatterjee from IST Austria, Thomas Meggendorfer, who is at Lancaster University in Germany, Leipzig, and Georgian Nicolette, who is at Singapore Management University. Both of them were at Austria when this work was done, and I was in India. Right, this one thing I mean I quite like about it is that this is really work with, which will combine hopefully these two papers that we had last year in CAV, which is like the formal methods paper, and INSCAI formal methods conference, and INSCAI, which is an AI conference. That should also tell you that this is a talk which is going to try to kind of somehow bridge some gaps, right? So that's kind of the goal of this, and yeah, let's get to it. Right? Okay, so yeah, everybody knows Markov chains, and we could have a Markov chain which describes the mood of this audience. Let's say there are 4 states. This is a transition system, and to make it a Markov chain, you have probabilities, right? So you have maybe 1/4 of you have not yet started checking mail because it's too early in the course, but it will happen, right? We all know this, right? So there's some probability with which you will do all this, and then you will go to sleep, or you will be interested, and so on. This is a Markov chain. We all know this, right? So
Are you assuming the initial state is interested?
initial state is definitely bored, right? That is the default state of people. But yeah, essentially the point is that you have this Markov chain, which means that the probabilities from every state, the outgoing probabilities must add up to 1. We are all familiar with this. And of course, the defining property is this memorylessness property, which is that the transition probabilities only depend on the current state, not on the history, right? Well, that is true for this data. I will leave it to you, but that's at least
The weight out of board is 1.1.
Yeah, for instance.
Sorry.
Thanks.
No, by 5 plus half.
Yeah.
2 by 2 by 5. Oh, I don't know which one is 2 by 5. Oh, that half is that.
Yeah. Thanks. It's between doing the verification.
He's in the interested state.
Yeah, it's certainly in the interesting category. Yeah, that's excellent, right? So once we have this Markov chains is clear, everybody, right? We can lift this to MDPs, right? What are MDPs? You have a Markov chain, but you have, other than probabilities, you also have non-deterministic choice, right? So here is an even simpler Markov chain. Now I have abstracted away from board, non-board, and all to PQ and RR states. Really, the non-deterministic choice here is only here, right? So there is an action A which is taken with probability 1, which means that you're here, and with probability 1, you may go forward, right? And then there is these are all deterministic states. So Q is a deterministic state, and at R, you have a probabilistic choice. So 0.5 probability, you state R, otherwise, 0.5 probability, you go back, right? And if you fix, you resolve the non-determinism, right? If you fix a policy, it gives you a Markov chain, right? So, for instance, if I say that I fix going right B, and then that gives you 1. But I can also fix the policy to be a randomized policy, right? So I can pick, like with half probability, I will be at P, and with half probability, I'll take A, and half probability B. Right? So you get a finite Markov chain. So, for instance, this half probability picking A and half probability picking B will give you this Markov chain. Right? This everybody knows, right? So I hope so, but just kind of setting up.
What is the policy? What does it mean?
So the policy here is just memory policy is just saying that at each state, what is the distribution over the actions? A memory full policy will say, given my history, if I am at a certain state, what should I do?
But that was also there before.
It's no, there is no policy in the Markov chain, right? Because it is purely probabilistic.
Okay.
There is no decision making happening here. Here there is decision happening, right? Because you have to, if I give you just this, there is a decision. At P, you make a decision. Do I take A or do I take B?
Okay.
Right? Once you take the decision, it becomes a Markov chain, right? And the policy tells you how do you take the decision,
Okay.
right? So a memoryless policy will just say maybe at P always take B. This is the memoryless policy,
Okay.
right? Or at P with toss a coin and with half probability do an A and half probability do a B. This is a randomized policy, and that's kind of right. All right. So this is one view, right? This is the standard view of Markov chains. But I mean, you can also just view this rather than as being a distribution over states, as a distribution, as a transformer over states. You can view it as a transformer over probability distributions. Right? This is not very surprising, right? I mean, given the initial distribution over all the set of all states, right? You can say, okay, if I give you a Markov chain, which it uniquely tells me which distribution do I do. Right? It's a deterministic system once this happens, right? So in particular, if I take 1, 0, 0, you can see that this Markov chain will go to half 0, and then it will go to 1 by 4, 1 by 4, 1 by 2, and so on and so on. Does it make sense? Right?
But the Markov chain is well mixing, then no matter what initial distribution is, it will be this.
Excellent. You will eventually converge at some point to one particular distribution. But what we are interested in not limiting properties, we will be interested in properties along the way.
Convergence.
Transient properties, not convergence, transient properties. And the properties we will be looking at will be more practically useful properties like safety or reachability or reach avoidance and these kind of. We are coming to that. That's exactly where we kind of bring some logical angle into it. What are the kind of properties we can talk, right? So, but before we go there, so given an initial distribution, this distribution you get a trajectory, and if I give you an initial distribution and a policy from the MDP, you can define the same trajectory because policy resolves the non-determinism, and then I can do the same. Right? So our goal, answering Ankit's question, is to reason about the properties over these trajectory of distributions. That's really what we are interested in this talk. Right? So this is orthogonal to the usual view of at least Markov chains and MDPs in verification, which is uses something called the path-based semantics, which if you're not aware of, let's not go into that. But just to say that there is this very classical logic called TCPL, right, and or PLPL or whatever it is, and those are all considered as path-based logic. This is different from that, and in one way you can easily see that it is different. Will be that you can show that, and this is classically known that checking PCPL properties is all polynomial time, and you will see that our problems are slightly of a different hue. Okay, so if you're not aware of this, it's not very important.
So here time is with respect to what?
Discrete time. At the moment, we are just talking.
No. You mean like to check whether a particular property is satisfied?
Yeah.
What is the input?
The Markov chain
The Markov chain.
or the MDP.
So the size of the state.
We'll come to that. Yeah, we'll come to that. The state space of the MDP will be part of your case.
And maybe the initial distribution is also part of
Initial distribution. We'll have variants which are hollows. We'll come to that, right? So I just want to say that though this exists, this
the strategy is memoryless, then it's the state space is not just the space of probability distributions over the state. You need more information.
you need more information to do what?
To even like to go to the next state. I mean, it's not a dynamic system over just this.
If it is numerical.
Yeah.
Yeah.
So it's okay.
We'll come. We'll answer all these questions, right? We're just setting up at the moment. So I'm going to come to the formal problem statement only about 5 minutes down the line. So this is basically, I just want to say before going to the problem statement, that this view of using this transformer, this is what I mean by the way as transformer of distributions. Right? It's really transforming distributions along the way. And this view, actually, there are logics which reason over this view also. And this has been looked at all the way from 2002, 2004. We had some work in 2012, 2015, which I may have talked about here many years ago. But and there is more recent work on this. So this is also a rich kind of line of work. Okay. So why are we interested in this kind of distributional properties, this trajectory on distributional properties? There are two kind of motivation I'm going to give. This is my only motivation talk, motivation slides. 2 slides you have to bear with me, and then we'll go back to theory. Okay. So one of the things is, if you look at, let's say the variation of a population of some, I don't know, some biological molecules over some time, right? And maybe there are some external things like markers, and under stress, what happens? And you can model these as an MDP, and you can say, okay, there is some non-determinism, which is like some switching mode that you have, and then there is some probability, basically, which is just transformation of some distribution which you have. So essentially, you want to say things like from this state, which is the state of some population of cells being in a high concentration, some percentage of this or some population move from high to low. And these are my transitions that I'm going to do. Right? And you can have modes corresponding to non-determinism. So in this case, what is this reasoning of over a trajectory of distribution giving us? It gives us ways to talk about things like this. From a given initial distribution, does the population of high concentration of marquees always stay above a certain threshold? Right? This kind of questions can be asked, for sure. I mean, this is just kind of modeling and existing kind of question into this problem, right? A more kind of
you go back to the previous slide.
Yeah.
So it's in one of the states, it is more than 5/12, or across all states you were talking about.
no, in one particular state. Yeah, I should have mentioned that. Maybe a high concentration of marquees. That particular state is it more than 5/12. I don't care what happens everywhere else. Is this one? So this is just a sample query that you can have.
And when you say that always, it's like irrespective of what non-deterministic choices that could be made.
That's right. So it could be that over all possible non-deterministic choices, or it could be does there exist a choice that you can make it happen?
Okay.
This is going to be very crucial as we go along.
Okay.
Does there exist a strategy, or is that strategy given, the policy given, or is it for all policies? And accordingly, the problem will change slightly. And actually, our solution technique at the end of the talk, if I get to it, will tell you a technique which can apply on all of them. Right? We'll come to that. That's from the biological or systems biology area. Another application, which is the one which we have in our HitScan paper. Now you know where the connection to AI comes in. Is on robot swarms, where you think about a grid world example. It's a classical example in AI. Right, and you have a bunch of grid, and where you have like some, I don't know, initial state, some goal state, and there are some obstacles. Okay, so there are, and you have some arbitrarily many robots in this grid, which start at some point and they move as time progresses. Right, and they are all distributed initially around the initial states. Some states, therefore, now if you look at the transitions in this grid, some will have some stochastic transition, some will have some static obstacles written by X. These orange states maybe are distributional objectives, which say maybe things like in that state, only at any point you cannot have more than 10% of the robots, right? So these kind of objectives can be there, right? And then you can say that the goal is actually to say that in this grid, does there exist a strategy such that out of this, you will start with all the robots here and reach the goal state while satisfying all these constraints given by this grid, such that you maybe 90% of the robots should eventually reach the goals. Right. So this again, you can see is nothing but a property, and here you see that it's very natural to ask this kind of properties. Can it be that starting from the initial distribution, you reach eventually 90% of the robots reach the goal, while in between avoiding some bad things? Right. This is classically the reach avoidance property. We will formalize all of this, but this is kind of to say that these are the two types of applications that you should think of when you're seeing why we are doing this. All right. Okay, and of course, not only whether you can, does a given policy does this, but can you synthesize a policy which ensures that you can always reach this?
But one issue seems to be that, so in this kind of a thing, you can only say things like, at some point, 10% of the robots were in a good state, and at some other point, 20% of the robots in some other state, and then finally 90% of the robots were in some state. But whether these robots were the same or subset, so that
will be, yeah, that's
the path, that's the path.
That's a part. Yes, that's right. Right, so that's different. I'm not saying that this particular robot did a computer. I'm just talking about the entire distribution. So in some sense, it captures some variant of partial observation in that. Right, you don't have the identity of that. Yeah, that's a good point. So basically, what we have done is the basics. We have looked at Markov decision process and this view of transformer of distribution. And what I'm going to do next. So this is the outline of the talk. Okay, so this is what we will do in the next. How much time do I have?
So 10 minutes, 5 minutes. So it's like 45 minutes roughly.
I have 45 minutes, excellent. Yeah, 40 minutes. 42 minutes. That's not quite excellent. 30 minutes, I'm going to 39 minutes. So we'll now go into how to formalize this problem and what are the properties of interest, what are the properties and problems of interest. And then we will look at some hardness results first, as we ought to, right? And once we look at the hardness result, we'll also look at hardness, kind of complexity theoretical hardness, and also why this need for memory, as Piyush is already kind of hinting at, gets into complications, right? What problems it gets into. And then we will look at positive things. So first the negative and then the positive, which is what is our approach to kind of actually deal with this. And this, we use this very nice idea which has been useful in invariant synthesizing invariants using inductive, so-called inductive invariants. And I'll try to see if I can motivate some of that towards the, and then finally we'll look at some limitations and future questions. So I'm hoping at least that we will cover 2 and 3 fully and give you a rough idea of 4. In 4, we can have a separate talk, but I'm probably here, I'm just going to give you like very hand-wavy things, but I'm hoping I'll give you some idea of the kind of algorithms, and then I'll leave it over for discussion. We can discuss more after that.
If you're
So,
Yes.
so the view of the state transformers is the one that you are talking about.
It's
PCTU.
Yeah, we don't do that.
So in what way it's like transforming states?
So it's a path-based semantic. You can think of that. It's like saying that the robot is in one state, then I want to go there, and they're looking at properties which happen as the tree there. No, you have this semantics there. So
Okay. So
it's yeah. Let's not get into that right now. We can. There are examples which show that view and this view are orthogonal in general. Right. Of course, there might be some cases where.
I was just going back to Piyush's thing. Even if you have only a guarantee on the number, because the robots are identical, can you say that a lot of them will have to be distinct with that probability?
I don't know. We haven't thought about that.
Because it's like taking IID samples with a replacement. So
Correct.
it shouldn't be all the same. Anyway.
Maybe. Yeah. Yeah, I'm finally going to now boil down to a Markov chain question and an MDP question, and we are going to deal with that. But at the end, we can maybe come back to this question of what does it really capture, right? Or maybe offline. Because I think there are different variants, and each time I give a talk in a different place, people see their problem in it or don't see their problem in it, or vice versa. Right. So there are, I think the problem framework is so general that many things can be put into it. But what exactly fits in is it's a great question, right?
So,
yes.
so this also means that the policies that you're making are the memory for the policy is the distribution that you have seen so far.
Sir, you are too fast. You cannot be so fast, you have to wait. Okay. So we will come to exactly this question about like half an hour into the topic. Okay. But yes, what is going to be this? Don't spoil my suspense, wait for it. Okay. Yeah, no, we will answer your question, or at least address some part of it, and then you can, at that time, we can discuss. All right, great. So let's move on here. So, okay. So what is the formal problem statement? So Akshay is interested in the input. Here is the input, right? So what you are given is an MDP. What you are given is also, so let me first zoom into one particular problem called the safety problem, right? Before we go into the general reach avoidance problem, we'll look at just the safety query. So we are given an MDP and we are given an initial distribution. Let's say we are given one initial distribution over the set of the states of the MDP. And you are given a set of another set of distributions, termed as H, which is the set of safe distributions over the set of states of the MDP. And we say that an initial distribution is H safe with respect to the safety set. If there exists a policy, here I am quantifying, I am looking at this particular variant where there exists a policy such that the resulting distribution always remains inside H. Does that make sense? Is that like formally specified? So this is what this means. For all I want that M under pi, this is just the notation to say the MDP resolved by the policy pi, right? Starting from mu0 in I steps. So for all I, that should be inside H, right? Now, the only thing which is not really specified here is how do we specify the set, right? What is the input, right? And in this talk, we will assume that H is given by a finite set of affine linear inequalities, conjunction of affine linear inequalities. Okay. So then once you have this, we will have two variants. One is kind of what is called the initialized variant.
You're going to show examples of this?
Oh yes, lots. Yes. We'll come to examples. But before I have examples, I want to kind of ask this question. So you can have two variants. One is I'm given mu0, the initial distribution, and I ask whether from mu0 it is H safe, or I can ask given just the set, does there exist mu0 such that it is H safe? Right? So these are two questions, and somehow it turns out that when H is the entire space, if I just ask, does there exist a distribution in not just a given set H, but the entire distributional space, then this problem is in fact polydimensional. And this we showed in 2018 using a fixed point argument, right? So this is actually an easy problem, the second one, which is a little bit surprising because it looks like it's a tougher problem, right? But the tougher problem is the first one, which is called the initialized problem, right? So we want to do that, and we want to ask whether if mu0 is H safe, synthesize a policy which makes it so. Or you can also ask, if you are given only M and H, you can ask, does there exist a mu0, does there exist a H such that it is, right? So all these are going to be the variants, but this is one particular specific variant we will pay attention to.
So if it's just a Markov chain, can you check these properties? That if you start from always units,
I don't know, we will see.
So-
Yes, we are going to come to that. Yes.
So the second one is always polynomial time.
No, with lots of restrictions. Like H must be the set of all states. It's not for a given set of states. But if I look at the entire distributional space, does there exist
So
any?
with the right properties, it becomes polytime.
Yes, with the right properties.
And what about the first one?
The first one I have not tackled yet. We are going to discuss this as we go along, right?
So you said which is always described as intersection of
Half spaces. So we'll come to that in a.
So that is for the second one also, like it's that restrictions where that it's the intersection of these half spaces.
It is a slight variant. Yeah. So it is some closed set. You will need some property that is closed and bounded, which is given. I mean, you can't have unbounded intersections. Here you can have, in the problem statement, you can have unbounded set also to begin with, right? Okay, I'm going to focus really on the first one, not the second one. Though second one also, I will have some comments to make at some point.
And in the definition of H safe, it's over all the states, like over
Overall the states.
all.
But it
the
can be
states,
some subset of the states also. It can be some subset also. We will see that. Let's give an example, right? Before I give the example, actually before the example, let me do two things. One is, let me try to generalize the problem statement, and then we'll go to specific examples, at least two examples I'll try to give after this. Okay. So the first generalization is that we can generalize both the safety point and we can generalize from giving an initial distribution, instead of saying that I start from a given initial distribution to looking at a set of initial distributions. Is that fine? Right? So, and you can basically, because I want to do reach avoidance, I will have not only a safety set but also a target set. So I have a safe set of distributions and a target set of distribution. And now the question that I want to ask is, the MDP itself satisfies TH reach avoidance under this policy pi if there exists an I. So there is some point where under this pi I reach the target set, and along the way I always satisfy or avoid. So I mean here I have taken H as the negation of the bad set. That is the avoidance property. So if you take the negation, then I want to stay in this set such that eventually at some point, some fixed point I reach.
Do you want it to be J strictly less than I or less than equal to I? Because you also say that at ith you are reaching T.
Whichever one you want. Sure, we can take less than I or less than equal to I.
So reaching T, if you then leave H, then you.
We don't care. Yeah, that's a good point. Yeah. We don't care. So we don't need to worry about what happens after that for the queries that we are interested in. But later, if you want to do general LDL, repeated reachability, then you will be interested in what happens afterwards. Right? So notice that this problem is on this mu naught, but the problem statement here does not have mu naught. It is over an arbitrary set of initial distributions. So of course, there are three variants. You can say either from a given initial mu naught, is this true? Or you can say, does there exist an initial point which is true? Or you can say for all initial points. So my point is just that, of course, all of this should be given by, again, just to keep it all consistent, let's keep all of them as affine linear inverse, right? And there are two problems again. We can also, here, this policy pi has not been fixed. So you can either say the policy pi is given and you're asking all these properties, or you can say that you are also trying to synthesize policy pi. Right? So essentially what I'm trying to say is that really there are multiple dimensions in which you can ask this question. You can change the power of policy, you can change the power of the memory within the policy, you can change whether the initial state, what is the property, you can change the target distribution, you can say change the safety to reach avoidance. So there is a lot to do. This is like a grammar that we are fixing. I don't want to go into exactly what it is, and that's something for future work, I would say. But this is kind of the framework that we are looking at. Does this make sense?
So you are not restricting to only memory-less policies, but it can.
At the moment, no. At the moment, I have not restricted to anything, right? But if you we'll come to this point. I mean, are memoryless policies really required? This has not been established, right? Like if you look at normal, MDPs and just want to optimally reach some state, maximize the probability of reaching a state, you know that memoryless and even not randomized, deterministic memoryless policies suffice, right? So there are queries for which you can prove that deterministic memoryless policies suffice. In this case, we have not yet shown whether it suffices or it does not. So that's something we will come, and I'll try to give an example to show you that in this case you cannot do such simple things, right? Okay, so now coming to your question. So the first question is, why even go to MDP? What about Markov chain? Does Markov chain makes this question much easier? So what would be the simplest question for a Markov chain? You are given a Markov chain, you are given an initial distribution, and maybe some. Let's say this is just state one is one of the states in the Markov chain. Okay, the probability to the question I'm asking is starting from mu naught. Is the probability to be in state one almost? Always at most some given rational. Okay. This is of course a plane, because why? Because this is the hyperplane that I have given here is set of all distributions such that distribution at the ith component is less than r. That's the hyperplane that we are looking at. So this is in our problem format, right? This is an easy version of our problem. And given a distribution mu naught and Markov chain M and H and the safety set H, we want to ask, which is given by this hyperplane, for all n mu of m power n is integers, right? So what do you think about this problem, right? And well, I shouldn't do this, right? There are too many people in this audience who know what's coming, right? So it turns out that surprisingly, this problem, which looks much simpler, is still open, right? And this is the famous, there is this famous problem called Skolom's problem, which is related to this. And it's a problem called there's a related problem called the positivity problem on linear recurrence sequences. Which it turns out, and in 2015 we showed this. It's a very simple 8-page IPL paper. If you're interested, I strongly recommend you go take a look at the proof. It's very small result, which is basically saying that this Markov chain problem, which is really a safety problem on Markov chain, is equivalent to, or at least as hard as, this long-standing, at least, I don't know, 50-year-old positivity, more than that, no? 100. Yeah. Oh yeah, Skolem is 100, but positivity was not defined at that time. Nobody cared about it until some point, but then it started getting defined as well, right? So there are related problems which are also 100-year-old. Problem on linear recurrence sequence. And what is this problem? Just so that others are not lost, there are 2-3 people who know what this is, right? Which is the positivity basically says, positivity problem, there is one framework where one stating of it, it says that given a matrix A, is A power n ij greater than 0 for all n. Okay, and it turns out this is equivalent to saying that given a LRS, a linear recurrence sequence, like the Fibonacci sequence extended with the coefficients being any linear constraints, coefficients, asking whether do all the entries stay above 0, right? And this problem, as you can see, is also already a very surprising problem. So once you see this, you're not so surprised that it's actually as hard as this, right? So the surprise is not so much that the Markov chain problem is hard. The surprise is that the positivity problem is hard. And how hard is it? Well, till now, the best known solution for the positivity problem is for rank 5 matrices. Matrices of rank 5, and it has been shown in 2014 by Wagner and Morel that if you could solve this problem precisely at rank 6, some Diophantine approximation results, which can be seen as, I don't know, 300-year-old open problems will get solved. Right? So basically, this is just saying that these problems, we don't know what is the status of these problems. So these are really hard problems. And
sorry, I mean, at rank 6 would imply meaning if you can solve this problem, if you
can show it's decided.
It's decided.
Then
it would give us some, what does this
number theoretical results,
which are also decision problems, or which are
they are not decision problems, they are some approximation problems. Can you approximate a transcendental number by a rational number up to some bit count, some precision and so on. So these are again results
sound sort of non-algorithmic problems. So you're saying somehow an algorithmic resolution would yield,
yes, that's
what sounds like a non-algorithmic problem.
Correct. That's what I'm saying. That's exactly the point. That's why it's, again, that was the best paper award in ICAL 24. Right? And there's a whole line of work. If you want to look into this, you can get, I don't know, buried in it for years. And it's a very nice problem if you're interested. But yeah.
But this is also not algorithmic, right? Because he's not talking about time. He's just talking about
No, but it's a decision problem. It's got an algorithm which can determine.
Right? Yeah, but the thing is, the algorithm itself could be a structural. It's just, if a certificate exists, it's of at most this size.
It's not completely amazing, but it's
something. Sure. Like by that.
Even the fight thing is of this kind. Like
actually, even the fighting is of that kind, right?
what do you mean?
It's like it's based on
very
deep, like very like sort of tight connection to this same kind of.
No, meaning like the positive resolution until rank 5 was already given number theoretical.
No, it's based on things that are like
the other direction. Yeah. The other direction is much more predictable. This one is less.
Yes. It was quite surprising when it came out. The proof is quite nice.
You can use number theory results to gain insight into structural things.
Yeah.
But the other way.
I'm just keeping going.
Try for all in
If
it's over.
Okay, sure.
Okay.
Yeah, if you put therefore, so it's then you solve the problem, right?
Oh,
Okay. So, yeah, I mean, we don't know whether it's both. It can very well be both, but we don't know.
The counter examples typically can sort of.
Yeah.
So the problem is just is there an algorithm, not is there a polynomial time?
No, decidable itself is not known. So therefore, this problem also, which we are looking at, is actually a super hard problem. We don't even know decidability, forget complexity.
We
Okay?
had an FSTTCS talk on this sometime, right? Remember?
Yeah.
20 or 21.
Yes.
The counter example was something so.
Very, very nasty. I think who gave that talk? Joel only gave it. Yeah. Yeah. So anyway, I mean, you should call. Maybe Piyush can talk about this, or I can talk about it at some other point. It's a very nice problem, and we have some very nice results also now. Maybe Mihir also visited here and gave a talk on it, which is the similar problem as this. Anyway, let's not go there. Let's get back to our problem. This is all just to say this is very interesting, and I still have to tell you my problem and how to solve it. Right, we have a long way to go. Right. So bottom line, I just wanted to say all this to say that this problem is hard. Okay, so you cannot hope for a very easy solution. So I talked about safety, but the reachability problem actually reduces to the Skolem problem. So called Skolem problem, which is whose history is even more kind of surprising, and this is a problem which Terence Tao calls as a mathematical embarrassment. Oh no, that's Richard Whitton who calls it a mathematical embarrassment, but Terence Tao has a long blog post on it and so on. So very tough problems, right? All I'm saying is that therefore it really, this simple looking problem that we are looking at is already a very difficult problem itself.
So
Right.
so here if you look at the other two variants, like if I allow you to choose mu zero or if I ask you for all mu zero, is that any easier, harder?
So that's a very good question. So if you allow me to choose mu zero, it does become easier in some cases. But if you are given a hedge, which basically, I mean, there are some cases which are easier, and most cases are still hard. Okay, there are some robust cases. You can ask, if you fix a ball and move around that ball, then we have some nice results. And this is work with Mihir Vahanwala and a few others, which was Stats 2022. There's a journal version which is out just last month. Yeah, so there are interesting results in this direction, but again, not our interest in this talk, right? Okay. So what I want to do in this talk is to look at examples. So I promised examples, so here are the examples. The same one which we saw before, but now I'm going to give you the safety query, and you're going to tell me what should be the policy which is taken, right?
Before that, so in this representation, are you kind of assuming that the decisions they are only like these letters A, B, these are only countably many, or can I have a finite
Propositions. Yeah. Right. So here is one problem, but you can have a randomized combination, but finite time.
Yeah, so the vertices are many.
Yeah. Right. So here I am taking the same one, but my initial distribution now is 1/3, 1/3, 1/3. And suppose the safety set is mu of R, the probability mass in the state R must be at least 1/4, 1/4, 1/2. Right. So if this is the query, what should be the policy that we should choose at B, such that this safety
Always take B.
always take B, right? Because if if I take A, then I don't know what happens. But if I always take B, how do you? Why do you guess this?
You go to R.
You're pumping more mass into.
Correct. You keep popping more mass, right? So you can already see that there is something in it. So this is very trivial, right? Everybody agrees that taking B is the right thing to do, right? You can make sure that the probability at R. But suppose I tell you, prove this formally, right?
What's the point of having Q in there?
No point. I just want to say there is one state in between and go there. I can maybe reduce the example and so on. It's coming. You'll see 1 minute. Okay. No. Let's stick with the program, right? So here what I'm asking now is how do you prove this? How do you prove that this is correct? This is going to be intuition for later part in case I don't have too much time in the algorithm. So one way to prove this is to actually say that I prove by induction. I notice that the probability in state P is always less than equal to the probability in state R if I use. Right? And I started with 1/4, so I'm always going to be above 1/4. right? And something like that we can try to show, right? So basically, it requires some inductive argument to prove this formally, right? Though we can see that this works, to prove it formally, we will require something which is talking about some inductive invariant you need to prove to then write it. Okay? That's kind of one observation I want you to hold on to, and we'll come back to it later, right? Yeah, so that's exactly what we did, right? Let's look at another problem. The same MDP, but now my initial distribution is 3 by 4, 1 by 4, and 0. Q comes in, right? It's 3 by 4, 1 by 4, 0. And I want the probability mass in Q to always be equal to 1/4. You can always write it, right? Greater than equal to 1/4, less than equal to 1/4. It's always equal to 1/4. Then what should be the strategy? If I take probability 1/3 B, remember always it should be equal to 1/4. So first time maybe you will get, no, even first time with 1/3 if I take probability, even first time I will.
3 by 4 times 1 by
Oh, 3 by 4 times 1 by 3 will be 1 by 4. Ah, right. First time we'll get it. First time I'll get it, right? But the second step,
I mean, needs to change.
needs to change. But what does it mean it needs to change? Needs memory. In fact, you can see that memoryless policy will not work for this. Exactly, it's always dissipating here. So, how do you tell at P? I need to know what the probability mass is, or I need to say that basically at here is one thing I can do. Choose A with probability 1 over 2 power I minus 1 plus I. You can work it out. I did, right? At step I, then this will actually be such. I just calculated how much mass needs to be done, right? But this is a memoriful policy, right? And you can see that memoryless, at least deterministic, it's easy to see no deterministic memoryless works. But you can also try to convince yourself that no randomized memoryless also will work on this if it's memoryless. So you need memory. Again, do you need finite memory? I think even with finite memory, you can't solve this. Finite deterministic, you can't solve this. But even finite randomized, you can't solve this. So it really needs something else, right? And this is going to be something which we are interested in, right? So what do we need? What is it that we are? This comes back to I think Piyush's question from the beginning of the talk, or Piyush or RP, no RP's question, I think, right? What do we need to know such that we can solve this problem, right? Of course, right, if I know which step I am in, but that is infinite memory. Which step I am in is literally the definition of infinite memory, right? But do I really need to know that? I only need to know the distribution in P, Q, and R at some point. That is enough to make me tell you how much mass to pass. Make sense? Right? So it is memoryless, but it is distributionally memoryless. But it's not memoryless as per the memoryless we are used to. Right? So that's kind of what we define as we go along. Okay, so okay, great. So with these observations, now we can go into what is our algorithm, right? So we have all the components ready
For
for
extra state is that. So it is still the state is still the only distribution, but you're allowed to depend upon.
Yes.
But it is not a policy in the usual sense.
It's not a policy, it's a new type of object. Some new creature is there, and we call it distributional policy, for lack of a better word. But yeah.
So sorry, but this Markov chain, this had this non-deterministic.
Yeah.
Oh, the Markov chain you already have.
No, this is the
Yeah, but there is this sort of a non-determinism, and you need a policy, right? Suppose you were given a Markov chain, then
then there is no policy.
there is no policy, and
Yeah, then it's only a verification question, but that is already still hard, right?
that's already hard.
That is already hard,
Yeah.
but I'm saying the policy question is also interesting, and policy question, at least you can see that memory is needed. So there are many interesting bits to it. The verification is already hard, so that itself we can sit and write, try to write papers. But the more interesting question from an application point of view would be to synthesize policies, and there you have all these tricky things that memory. It's not like usual MDPs where and the optimality questions where you don't need memory, right? So the problems are slightly different here.
The dynamic constant picture, it's not really a memory. At each point, you have a different, you have a function, which so depending on the point, only certain functions are allowed.
That's right.
It's only certain so ft plus 1. The next generator will depend upon the current.
Yes, that's the only difference. That's the only difference, and we will use that to provide our algorithms, right? So finally, we have to. I mean, we know that problem is hard, so we can't solve the problem in general. We don't try to solve the problem in general, right? We want to actually try to restrict something. So what do we restrict becomes
No, wait, sorry, go
Yes.
back. So even in your formulation, you could have, if you are saying it's a function of the distribution, what could be happening is that the probability mass is some real number that captures the entire history. So so currently it's nice rational, but if I give you some weird transcendental numbers, it is actually capturing much more than what you need.
You're very right. Without the policy itself, it is hard, right? That's what I established already so that you don't ask this question. Because without policy, just when you have Markov chain itself, the safety question is as hard as the positivity problem. So we can't anyway hope to avoid nastiness, right? What we are, the only thing we can hope to do is apply some restrictions on something so that we can get solutions.
But I think it's not a restriction because if you have some.
No, but the thing is, you cannot transform that in arbitrary way. So you cannot propagate that information forward.
I still can, like
It's
I'm
just
pretty
linear
sure.
transformation alone.
Linear transformation, yes,
There is
but the linear transformation, the value, if I take two transcendental numbers, I think the value will capture everything that has happened so far.
But it's not like the arbitrary linear transformation also. It has to be one of the like a finite sort of.
Yes.
There's only finitely many matrices that you have to choose from at each step.
Yes, that's correct. Yeah. Because this comes back to your question that the number of A, B actions are only finite.
Okay.
But you allow randomization also, right?
Yes.
So
Yes, a convex combination.
Convex combinations are
Yeah.
finitely made. That's right. It's not finite
Okay.
when you have randomized, but they are nicely behaved. But that doesn't help you. That doesn't help you in general, right?
Okay.
Okay. So let's see. I mean, faced with these challenges in the next 10 minutes, what I can do. So yeah, this is what I was afraid of, but I'm ready for it, right? So I'll try to give you a high-level picture of this and just deal with the memoryless case, and everything else we will leave for further discussions or part 2, right? Okay. So let's see where we are now. Okay. Yeah. So 10, 12 minutes is good. Okay. So first observation is that we are going to look at certificates. So this is where I mean, if you have seen the policy, the abstract, there is things about certification there, and we will define this object. So I'm going to make 2 definitions, and then we will look at some properties of these things. So we are going to look at distributional invariance. What is a distributional invariant? Given an MDP, given an initial distribution and a policy, we say that a set of distributions is a distributional invariant if I mean whenever for all I, if I apply from U0 I stay in this side. Okay, this is a distributional invariant. It's just a definition. I is inductive if I start from I and applying m pi puts me back in. So this is the invariant inductive. So both together it's an inductive invariant. Okay. I need another definition, and after this I promise there are no more definitions so much. Right?
So what is delta of S? It's
Set of all distributions. I think I used the same notation before, so I used it. Right. So we are now defining just what we said already. I think we have already discussed this distributionally memoryless policy, which depends on the entire distribution and tells you where to go next, right? And what we will actually show is that these policies, in fact, suffice for safety. So what you can show, and this is not a very tough proof at all, 5-line proof, which says that mu0 is head safe if and only if there exists a distributionally memoryless head safe policy pi from mu. Okay. In interest of time, I'm not even going to go into this, or should I? So basically, the idea is easy to see. In one direction, of course, it's trivial. In the reverse direction, in the forward direction, you essentially try to go along, and if you are repeating things, you define the distributionally memoryless policy by looking at the distribution and then saying what actions should be taken. Right? So that's all. It is not a very difficult proof. This is not the interesting part. Right? But what is interesting is how do we link this to the distributional invariant? And what you can show is, oh, this should be also there exists. So there exists a memoryless, distributional memoryless head safe policy, if and only if there is a policy and an inductive invariant such that that inductive invariant is in H. And this also is not actually a very difficult proof, because you can again see that how do you build this invariant? You can just see from the initial point where all you reach and put that as your invariant. And you build that as the set of invariants, and you can see that that will satisfy all the properties of being an invariant. So somehow this is very nice. We reduce the problem of H-safe into a problem on distributional invariants, but these things are equivalent, which means that we cannot solve this one either. Right? All this means is that I have reduced the problem to a problem on inductive distributional invariants, but this problem is as hard as the original problem, because actually the point is that this shape of this inductive distributional invariant can be arbitrary. We don't know what that looks like, that object looks like, right? And so that tells us an idea of what to restrict. So we will not restrict the characteristics of Markov chain, the MDPs, initial strategies. We will not restrict what memory we should use, block memory we will restrict. Everything else we will not restrict. But what we will restrict is the shape of the invariant. We will say, can we come up with an inductive distributional invariant which is actually just affine? Okay, this is the problem actually that we will solve. Because the general problem you cannot solve. I mean, you can solve, but then you will solve like lots of other very interesting problems in number theory, right? So this is the problem that we will actually solve, which is basically to restrict to affine linear inequalities, and for these we will set templates and finally use a solver to synthesize these invariants. So that's really the very high level one line idea of it.
For the earlier problem, is there also reduction from positivity in the other? Like, are they equal?
So it turns out they are equivalent. Yes, it was shown later. It's not very difficult to see that they are equivalent, but it requires a move. Even Markov chain, I think, is equivalent. To school them, at least there is.
Okay, so really, what this it's about just taking eigenvalue, you're just taking data. So
Yeah,
it's similar.
For the case of the Markov chain, also there are problems like if you restrict your range to certain classes, then the problem becomes solvable or easier.
yeah, because I mean, we are solving for MDP itself, so that also gives you a way to solve for but how do we solve, right? What I mean, it still hasn't given the solution. It's just that finally what restriction I'm looking at to get solutions, right? So the algorithm is going to be in 4 steps. Okay, so this is perhaps this and the next slide, if you bear with me, and I'll be done with the talk and we'll move to the limitations. Right? Okay, so let's try to go through this. This is going to be a little bit technical, so definitely I can't do it in 6 minutes, but we'll see how much we can do. Right? So our idea is first we will set up templates. Okay, so I'm going to do it in 2 steps. I'm going to give you the high level idea of the algorithm in 4 steps, and then we'll try to do it over one example to see what it looks like. Okay, and that example will be a special case. Right? So we will actually, what does it mean? It basically means that we use symbolic variables to represent pi and I, right? And these invariants are coming from, now we have restricted them to affine linear inequalities. So those coefficients of that equation will be our variables, right? We will collect all those constraints and we will find out, we will prove that actually this gives us a problem in basically the general theory of reals. But then we will apply quantifier elimination on this to get a problem in existential theory of results, and therefore we will finally end up showing that we can solve this problem in existential theory of reals, right? And then we will actually send it to a SMT solver over an array to actually synthesize this. So that's really the idea of this, and it works for small examples. Tomorrow somebody builds a better SMT solver, it will work for bigger examples. Right, that's kind of the idea. To reduce it to problems. This is a kind of a powerful way of doing things. Hoping, and this also gives us nice ways to give benchmarks to these SMT solver people to improve their tools. And this has been very successful in SAT solving, and now people are trying to do it in SMT solving as well. So that's going to be the broad idea. Okay. So before you ask me what these things are,
are they like two alternation of order? So
yes.
For all, like
for all there exists. So it will be a second order quantifier. That's exactly what I'm going to do. We will need one trick to make it to a first order, to an existential theory. And that is an important trick. Without that, there is no scalability. Everything theoretically is all fine, but there is no scalability. The actual tools are there only for existential theory. So if you had for all that exists, you can't do anything with it. Right? Well, maybe you can, I don't know, at least nothing scalable, right? Basically look at this, so first of all, I mean in this case, let me give you an example, but I'll give you an example for memoryless policies. Okay, the policy will now be memoryless, but the invariant will be linear affine invariant. I know that this problem is easier, but this is the easier one to explain as well, and more details you can read the paper to see how we generalize to a more general form of policies, right? So first notice that if it's a memoryless policy, then actually for the policy, the template for the value is just y of si. Basically at every state, every action, I need to fix one variable. And for the template, I will have something like this, right? All the variable should be a distribution and satisfy some affine things. Conjunction of some bunch of things, but I don't know how many, so I will try 1, 2, and so on. Right? I will just hope that there is some number at which it will work. That's what we will do. Right? And then we will build constraints. The phi init will check that the initial distribution is an I, and we affine this expression over mu0 is greater than 0. So this is a little bit abstract. So let me just give you the example rather than here is the example. So for instance, what I mean is that for this example, the initial, so I have these variables x0, x1. The initial distribution is 1 by 3, 1 by 3, 1 by 3. So it really gives rise to a constraint of this form. And here you can see what Piyush had already kind of guessed, which is that for safety, what you need to check? You need to check that for all x, if I'm in the invariant set, I am safe, right? There is a quantifier alternation here because I will ask that do there exist such values for all these coefficients such that for all x blah 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 happens.
So x quantifies over this x here. X is a
here x quantifies over all rails, right? Because I want for everything inside my inductive invariant to be safe, right? Similarly, the inductive invariant itself says that for everything in I, if I apply m, it should be inside I, right? I of x implies I of next of x, right? And then there is a strategy thing, which is that I need to check that each of these is a distribution over actions. So there are a bunch of them. So, but you can see the important point to note here is that some of these are existential quantifier because I'm going to basically ask, does there exist x0, x1, x2, x3 such that for all x and blah 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 this happens, and so on and so forth, right? So does there exist y?
X0 here is the coefficient in the affine.
Yes. I know that.
And that x is different. That x is
some notation I should have fixed there, but yes, that x is different from the x0 that we are looking at here. But basically, the bottom line is that I'm asking for does there exist a SI and does there exist all these parameter values such that this formula is right? And now the point, as I said, this is these two are universally quantified, but now you can use Farkas lemma because these are affine linear invariants, and Farkas lemma will tell you that you can reduce it to existential. And with new variables, you'll have a bunch of more new variables, but that's kind of at least reduces to something where you can then send it to a SMT solver. Today's SMT over real arithmetic, and those will give you a solution. So that's kind of the idea. And what is the theorem that we can actually prove that if there exists a memoryless policy and if there exists a affine inductive distributional invariant, so showing safety, we will find it by just increasing this ni. We will find it. If there exists one, we will find it, and whatever we find will always be correct. So we have soundness and we have what is called relative intelligence, right? That's kind of the technical part. So now I just kind of hand away all the complications. So we can generalize this. In fact, we can generalize. How much can we generalize? Because linear invariance sounds really too simple, right? And it is too simple. Right, because it is sufficient for memoryless policy, but it's not sufficient in general. And in fact, what we can do is we can even do quotient of affine expressions. And it turns out that that is really super powerful. In fact, the example that I started with, the one which required infinite memory, that I can solve using the quotient of affine expressions. I'm not sure I'll have time.
So why is it not like you?
Yeah, I will send the other side. So now
one extra.
It becomes polynomial, that it becomes x squared. You will have polynomials there.
So these are what cross terms will appear.
Yes, some quadratics will appear. Yes, so things become easier. Difficult, and you can't use basically Farkas lemma. That's where things break down. You can still get it at for all there exists some something, but you can't. You have to do something more. And there it turns out that you can do quantified elimination by using the special structure of this formula. You can do quantified elimination using this so-called Handelman's theorem. Again, I have 0 time now. Can I have 4 more minutes?
Sure.
Yeah, I'll try to finish my in 4 minutes. Right. So basically, we use ideas from basic algebraic geometry. I think. I mean, this crowd probably I should not even call it that. It's this Handelman's theorem to say that I can actually get rid of these quantifiers as well. It turns out that doing that, we lose completeness for some very corner cases we don't know yet how to fix, but we do retain soundness. So whatever you get will be correct. So therefore, you can do this, run it to a solver, and if the solver gives out an answer, you are guaranteed that it satisfies all the safety constraints. Right, this is kind of where I stopped. So we did implement this in Python, which calls Z3, which calls MathSat, it calls a bunch of things, and we can actually synthesize these things for the example and a few more examples that's there in the paper. But there are many questions. There's a whole bunch of artifact evaluations that went through at some point of time last year. It turns out that we can also lift this all these ideas from safety to distributional reach avoidance, and that's the topic of the paper, where we actually show that distributional memory-less policies also suffice for reach avoidance here, but the notion of certificate changes. It no longer suffices to have an invariant; you also need a ranking function because you are doing reachability also, right? So you need something to ensure progress towards the goal. So you basically keep a pair of objects, which again we will restrict to being linear, but the pair will simultaneously go towards the target while remaining in the same set. That's really the core idea of this paper. And yeah, there's a typo there, but yeah, we synthesize affine invariants, affine certificates, and we can do these things. Yeah, so that's kind of where I'll kind of end this. So that brings me to my last slide. So there are many questions here, right? This is really, I think, setting out an agenda, and we try to kind of set it in 2 communities. But the hope is that more people will get interested in it. So, for instance, can we extend from templates to general polynomial expressions? Turns out you can, but you need variants of positive null results then to kind of solve these problems, and those are not scalable. Those won't work in practice. So if there are there have been people throwing around words like semi-definite programming and so on, which I don't know how to use, right? But probably that's the one way out, and there are people I think working in this direction. This question of uninitialized case, strict guards, there are many things which come up. For the logic community, there's this question of can you go beyond reach avoidance into linear temporal logic, the full logic. And we think we can, we are working towards it, but we don't have a solution yet. What is a more theoretical, maybe fundamental question is, what is the power of linear and polynomial invariants? We know they don't suffice. We know there are policies, but actually, in fact, we don't know. For some of the reach avoidance questions, I don't know whether linear or polynomial invariants suffice. Even for safety, I don't know whether polynomial invariants always suffice. We don't have examples, explicit examples where we need more than polynomial. So it's a very funny situation, right? We know something is needed, but we cannot prove anything more than this, right? So that's kind of where we are. There are more higher level questions also, but I'll stop and talk here.
So do these questions change when you just something like if you're greater than or equal to becomes strict greater than or something doesn't change? Those things don't change. There's some variants of Skolem where that does, right?
Yes.
Yeah.
I think no. Not really. Is there some way?
The duality theory can change drastically, but or not drastically, but I can get all these kind of weird things.
Actually, it changes for our algorithm. The strict versus non-strict for our approach. There it changes lots of things. The problem itself, the Skolem part will not change. But indeed, for our algorithm, whether you have only strict or non-strict makes things different. Like when Akshay, when Handelman's work, all these are actually very sensitive to strict and non-strict inequalities.
This classification A to the M, other than rank, has anything else been looked at for the matrix?
Yes, we have done some work showing that if your matrix is structurally nicely behaved, like if it has only real eigenvalues, you can solve the problem in NP power RP. Right, and if it's a root of reals, roots of unity, you can it's NP complete. And if it is roots of complex roots of reals, then we can show something. Yeah, so there are a bunch of results, but nothing much more than that is known. So either you have to restrict the structure, the eigenstructure, or you have to restrict the rank. These are the only two much to the best of my knowledge, or you restrict the problem, saying make it robust. Like make it like in the initial you don't want. Does there exist something within the neighborhood such that this happens? So you allow some, or you allow some approximation somewhere else.
Oh, that
You have to do something like this.
That makes the problem easier.
Some variants of it makes it easier, some variants it does. So there is a whole line of work on this. Again, with some undergrad students here, we've done some progress in some of these problems. Nikhil Balaji also has worked on some of these problems with us, but yeah, that's kind of the basics.
So the template-based synthesis that you were talking about,
Yeah.
you were only looking at the memory-less policies.
No, it works even for this distributionally memoryless policies of the form, but we do need to restrict, but we will restrict to something like it depends on the current distribution that we can encode. In fact, we can encode that in distribute. Yeah, exactly. So that we can encode as templates, but as Piyush was saying, that introduces non-linear variables inside. So it no longer remains linear, even though you started with linear invariance, because you have these more complicated templates for the memory for the policies that introduces quadratic terms, and that's why you need to start appealing to more powerful theorems like Hamilton's.
So if there are other questions, if there are no more questions, let's thank Akshay.